Imagine you are riding a bicycle. So the wheel is rotating, the bicycle is moving forward. But here is an interesting question. Is the wheel only rotating? Is the wheel only translating? Or is it doing both at the same time? Today, we are going to discuss the physics behind this beautiful motion known as rolling motion. So, rolling is basically a combination of translation and rotation. Let's try to understand the physics behind it. So, imagine that wheel that I was talking about. So, let's say this wheel and its axle is located somewhere here, which is the center of mass of this wheel. So basically what is happening, that this is the ground on which this wheel is rolling. So the center of mass is moving forward, let's say with velocity vcm, and at the same time all the particles around it is moving in clockwise clockwise direction, let's say. Now if you wish to calculate velocities of different points on this wheel, what would be the correct way to represent it in terms of physics, right? So let's say if I pick the topmost point, let's say, let's call it point number A, right? Now if I wish to calculate the velocity of point A, what would that be? Now because this entire wheel is rotating at the same time, the center of mass is moving in forward direction. In fact, center of mass is the only point which has only translation velocity. The rest of the points has both velocities due to translation as well as rotation. So we have to keep in our mind that only the center of mass will be having this translation velocity, right? So imagine an observer who is placed on its center of mass. So he would see that all the particles are moving in a circular path with respect to the center of mass, right? But if you watch it from the ground frame, right? So what would happen? A ground observer would see that this center of mass is moving in translation with translation velocity, and rest of the points of the circle will be having components of velocities both due to translation as well as rotation, right? So let's say if I wish to calculate the velocity of point A, so what would that be? So let's say this is VA. So VA can be written as velocity of A with respect to center of mass plus velocity of center of mass with respect to ground. Now, why this has been written? We know from the concept of relative velocity that velocity of A with respect to B, let's say, is VA minus VB, right? So, if I wish to calculate velocity of course, this is with respect to ground, velocity of A with respect to ground minus velocity of B with respect to ground. If nothing is written, we will assume it to be in a ground frame, right? So, velocity of A can definitely be written as velocity of A with respect to B plus velocity of B with respect to ground. So definitely it has both combination. Here B is basically center of mass. You might call it the center of mass. So with this logic I have written this one, right? So velocity of A with respect to center of basically talks about, let's say the radius of this wheel is r. So this point, due to rotation, if you observe from this point, you will see that this point is moving in tangentially in a horizontal direction, right? So this point would be having velocity of r omega due to circular motion. We know for circular motion, any particle which is on its circumference, it will be having a velocity of r omega, right? And r omega would be directed along the tangent of the circle, which is at this point is directed along this direction. And due to vcm is again, it is vcm would be parallel to, of course, at all the points, the component of velocity of center of mass would be parallel to this one, right? So point A has two velocities, one due to center of velocity of center of mass and another is due to the rotation part, right? So point A, at point A, VCM and R omega, direction of both are matching. So what we can write at this point, let's say if this is x direction and this is y direction, right? So what we can actually write velocity with respect to center of mass, this can be written as This is r omega, right, along I cap, and VCM is again along I cap direction. So this would be VCM plus r omega I cap, right? Now, let's say if I wish to calculate the resultant velocity of point B, right? So velocity of point B, again we can write that velocity of point B would be velocity of B with respect to center of mass plus velocity of center of mass with respect to ground. So this would be again, now you have to be careful that point B, velocity of point B with respect to center of mass would be in vertically downward direction, right? So r omega would be directed along minus j cap in negative y direction. So this would be r omega minus j cap, and VCM will be always parallel to x-axis, right? So the component of VCM at each and every point would be directed along positive x-axis, while the r omega component, depending on which point on the circumference that point is there, accordingly its direction would be changing. So that's the main concept of this entire velocity thing, that we need to be careful about the r omega component, because VCM direction of velocity of center of mass is unique, but the r omega part, direction of r omega part is not unique, right? So here r omega is directed in negative y direction. So here we can write, of course these are in two different directions, so you cannot simply add these two like we did here, right? These two, both the components were directed along I cap direction, so we can simply add here, but we cannot do the same here because these two are in two different directions. One is along I cap and another is along minus j cap, right? Again, so this has to be, if we wish to calculate the magnitude of this velocity, we will have to use vectors to find out. Of course, these two are perpendicular, so you can write down root under VCM square plus r omega whole square ka root under, right? So that could be done. Now, if you wish to calculate velocity of C, so this would be like C is this point, right? So due to VCM, the velocity will be in forward direction, and due to r omega component, right, this would be in backward direction, right? The r omega component in backward direction. So for velocity of point C, velocity of C with respect to center of mass plus velocity of center of mass with respect to ground, right? So here the r omega is directed in minus I cap and VCM is directed in plus I cap direction, right? So effectively this velocity is VCM minus r omega I cap, right? Similarly, VD, if you wish to calculate VD, which is basically this point, right? And also you have to be careful about this, that here VCM, like at point A, the resultant velocity of point A is directed along I cap. Here, if we assume that VCM is more than r omega, in that case, VC would be directed along positive I cap. And here VCM is in positive I, r omega is in negative j. So resultant velocity will be directed along this direction, right? VCM is in this direction, r omega is directed in negative y direction. So of course the resultant velocity will be in this direction, right? And if we wish to calculate at resultant velocity of point D, again you can write velocity of D with respect to center of mass, right, plus velocity of center of mass with respect to ground. So here the velocity of r omega component would be in this direction, right? Yeah, I have forgotten to show r omega component here. So r omega would be in this direction and VCM is in this direction, right? So here we can write velocity of r omega component would be along plus j cap and VCM would be directed along I cap, right? Again, we need to calculate the magnitude of velocity of point D vectorally. We cannot simply add these two, right? These are vector quantities and these are in two different directions, right? So that has to be taken care of. So in this way, you can actually calculate velocity of any random point, whether it's here or here, somewhere else, right? So we have to find out the r omega component, we have to find out the velocity of center of mass component, and we have to add these two vectorally, right? So just you have to be careful, like here the angle between VCM r omega is 0. Here angle between VCM r omega is 180 degree. Here angle between VCM r omega is 90 degree, and here VCM angle between VCM r omega is again 90 degree. So of course these are special cases, not general one. So in general one you might have point anywhere like at any angle theta. So we need to calculate, like if the point is located at any angle theta, in that case VCM will be directed here and r omega will be along tangential direction, right? So of course if this is theta, this is 90 minus theta, and this is theta, right? And this is 90 minus theta. So in this case, let's say of any general point Vp, what you can write that root under VCM square vector, you have to add r omega whole square plus twice of VCM into r omega cos 90 minus theta, right? So this would be your resultant speed of any general point located at an angle theta with respect to horizontal, right? So you have to add these two velocities, VCM and r omega vector. That is the only thing you have to take care of, right? So this is basically rolling. Now there is again a special case of rolling which is known as pure rolling, right? So what does pure rolling mean? When there is no slipping between point of contact and surface, then we say that the body is in pure rolling. That is, there is no slipping. Like let's say this is ground, right? This is ground, this is point of contact. So basically C is your point of contact. So if I wish to calculate that this body is, let's say assume that this wheel is in pure rolling, so what we would write that VC, velocity of point C with respect to surface, is 0. Only then there would be no slipping, right? Or you can write that velocity of C must be equal to V surface. So these two are same thing. So like in this case, the VC is VCM minus R omega, VCM minus R omega, and surface is ground whose velocity is 0. So what we can write? This is equal to 0. So of course this is a special case, right? Where surface velocity is 0, but it may not be the case every time, right? So if this surface has certain velocity, then you have to write down that velocity. In that case, VCM minus R omega would be equal to V surface, right? And if you again, if you differentiate these two, you can again write relation between acceleration also, right? So basically in this lecture we discuss about what is rolling. We took an example of rotating wheel. We understood how its motion is happening on the ground. The center of mass was moving in forward direction. Basically axle is there at center mass location, axle is present, so that axle is moving in forward direction, and this is the only point which is having only translation velocity, while rest of the points around it on the circumference will be having components of velocities both due to translation as well as rotation. So for different points on the circumference of wheel, we need to write down their velocity vectorially, right? So sometimes it might be simply added, sometimes it might simply be subtracted, and there are times where it might be perpendicular, and there are times it could be the angle could be any value between 0 to 180, right? So accordingly we have to add vectorially, and we'll try to find out the resultant velocity of any point on the circumference of the wheel. And again, the special case of rolling is known as pure rolling, where the point of contact is not slipping on the surface on which the body is rolling. So if there is no slipping between point of contact and surface, then it is known as pure rolling, right? So that's all for today's video lecture.